let me just remind you, what we did. We started out by assuming just spherical symmetry in the metric, just saying that the metric had, one part of the line element which looked like d omega squared, and using that we were able to derive a rather unique solution. And the unique solution, once we extended it past the horizon, had this form which is called a Cosmological diagram. Okay, and this is what's called the UV plane. And this was the line u equal to 0. This was the line v equal to 0. Remember that these u and v coordinates were related to our original coordinates by means of, u is equal to e to the power r star minus infinity by 4n. V is equal to e to the r star plus e by 4n. R star. Can you just check if this is consistent with the conventions I used yesterday? I think it should be. Okay, so I think this is consistent with the conventions I used yesterday. I wrote down some metric in the dv coordinates, which I think was actually correct. Somebody objected to some of the constants in front, but actually I think the constants were correct yesterday. So I wrote down a metric yesterday with some 32 and cubed, but I think it was right. Okay, so in any case, this is just to remind you, there's some transformation of coordinates. The original r and t coordinates, the Schwarzschild coordinates, are valid only in this patch, which is called region 1. And then once you get the metric in these uv coordinates, you see that these boundaries, these horizons, which are equal to m, are just some coordinate singularities. And in fact, once you have the uv coordinates, you can smoothly extend the metric into these regions 2, 3, and 4. Okay. But there is a true coordinate singularity, which is at r equal to 0. I think the mic is going on and off. No? Is it okay? There is a true coordinate singularity which is at r equal to 0, which in these coordinates, is at in the conventions I've chosen here, is at r star equal to 0, and that's at uv equal to 1. Okay, so there's a hyperboloid here which is at uv equal to 1, where there's a true singularity. And the significance of these regions was that u equal to 0, even though it was only a coordinate singularity and had no local significance, was still a horizon. So it separates region 2 from region 1, and similarly v equal to 0 separates region 2 from region 3. And the significance of this is that once an observer crosses into region 2, there's no way to cross back into region 1 because you can't cross a light ray. Okay, so that was the significance of these things. The diagram as it's drawn here is sometimes called a Cosmological diagram. There's a more conventional way to look at the causal structure. See, one thing that's very important in our discussion of black holes is this issue of what the causal structure of these things is, and how different observers perceive the same set of events. So yesterday, for example, I described how if you had an observer here who went in to the black hole in a trajectory like this, this observer would fall into the singularity in some finite proper time. But if this person was sending light rays to somebody outside, he would send a last light ray from here. And after that, no more light rays would reach the person outside. So from the point of view of the person outside, it would look like this person was frozen in time. And to look at physics like this, it's very important to have this causal diagram in front. These causal diagrams can be presented in this way, but they are more conventionally often presented in terms of what's called a Penrose diagram, which tries to bring, even here you see that there are these infinities in the UV plane. So sometimes it's convenient to bring these infinities down to a finite distance, and that can be done rather simply by means of the following math. Okay. So you just use some tan inverse math, which will bring these infinities down to finite distance, and you see that u equal to constant and v equal to constant were light rays here. That means that chi equal to constant and zeta equal to constant are also light rays are null lines in these new coordinate systems. We don't even need to work out the metric in these new coordinate systems. All you're interested in is that chi equal to constant and zeta equal to constant are 45-degree lines. And you know how the graph of tan inverse looks. Maybe we even discussed it. We discussed something similar in the previous lecture. Now what tan inverse does is it maps things from minus pi by 2 pi by 2 minus pi by 2. Okay, this is tan inverse x. Sorry, it's merging with the black hole, but anyway. Okay, so this is it. Okay, so this is what tan inverse does. It brings the region from minus infinity to plus infinity down to the region minus pi by 2 to pi by 2. So first, without even drawing things at 45 degrees, let's just look at the plane, the region in the chi, whatever this is, zeta plane. And that you would think is the following region. See, first you might just draw a square, which is minus pi by 2, and then, so let me call this zeta, 2, chi equal to minus pi by 2, chi equal to pi by 2, and that chi equal to minus pi by 2. So this is right now just a, just the square, just that region here. Okay. And right now I've drawn these as straight lines. I'm going to rotate this figure in a second, but I just want to tell you how you get this in a simple way. Now the important point here is that this, this figure gives you the full UV plane. Okay. If I use this kind of mapping and I draw this kind of a square, this square gives me the full UV plane. Okay. But the full UV plane is actually not part of our physics, and that's because there is a singularity at UV equals 1. There's UV equals 1, and beyond that there's no region that goes beyond UV equals 1. Okay, so UV equals 1 is a statement that tan of chi into tan of zeta is equal to 1. Okay. So UV equals 1 means tan of chi into tan of... Okay. If this is the case, then this tells you that you can have two possible relationships between zeta and chi. So one of them is that zeta is pi by 2 minus chi, and the other is zeta is minus pi by 2 minus chi. So zeta is pi by 2 minus chi. You know that cos and sine flip if you take pi by 2 minus the argument, and therefore these are the boundaries in terms of this UV plane. So in terms of this UV plane, you see that you're going to cut off some regions of this diagram. And the regions of this diagram that you're going to cut off, if this is chi equal to 0, are these regions. So there are some regions of the diagram that you cut off. Those are these regions. So this, I think, is, I hope I drew it correctly, is zeta is equal to minus pi by 2 minus chi. Sorry, one second. Let me make sure I'm not getting my zetas and chi's confused. Good. Sorry, I should draw it better with this. It's a 45-degree line, so it goes from the point here to... And there's another line that does the same thing here. Okay, that's zeta. Okay. Anyway, so there's this, there are these lines which you cut off. Okay. The correct way to draw space-time diagrams is where null lines are at 45 degrees. Right? And in this thing, null lines are flat, and that's because we had this coordinate system which we chose, which was u and v. And I just wanted to show you the figure. But the correct way to draw this diagram is, of course, to rotate it, and then the diagram becomes this. Okay, and these are the horizons. And this diagram is sometimes called a Penrose diagram. It's really capturing the same information that Kruskal diagram is, but sometimes you'll see the diagram drawn in this way. Okay. And in this diagram, there's what's called past null infinity, which is this. Okay, this is past null infinity. There's a future null infinity. This is the future horizon, and this is the past horizon. Can you read it all? I've written here, past null infinity, future null infinity, future horizon, past horizon. Okay, this is the past horizon, the future horizon, and this is the singularity.
So,
yeah. How I made what? How I made these horizons? These horizons are so these horizons are the regions that okay, what do you mean by how I made? I mean they're the things that demarcate. They're global things. So they're things that demarcate future null infinity. So there's some future null infinity here. There's a question of when an observer can reach future null infinity. If an observer is on this side, there's no way it's possible for the observer to reach future null infinity. These horizons are just these lines. So they're these lines. So they're the lines which go from. So once you're inside here, there's no way you can reach future null infinity, and those horizons are just those lines. So it's just that diagram.
From the square, there u equals 0, which is flat, so it becomes a diagonal.
That's right. U equals 0 is this one. These are these lines. So when you rotate it, they'll become these. Okay. So this is what a Penrose diagram is. There's nothing very deep about a Penrose diagram. It's giving you the same information that the Kruskal diagram is giving. Often it's actually convenient to think of this Kruskal diagram, but sometimes it's conventional to think of the Penrose diagram. Okay. So that was what I wanted to say from yesterday, and this has to do with the causal structure of this black hole. Okay, so this this gets me to the conclusion of the static Schwarzschild black hole solution. Are there any questions about this part? Okay, so now I actually want to tell you that even though we're drawing this diagram, in fact most of these regions, these region 2, 3, and 4 are not really physical and don't appear in black holes that are formed from collapse. Now that doesn't mean that they're not useful. In fact, they are useful as toy models, and there are various exotic interpretations that people have given to these things. For example, this region 2 is like a wormhole between region 1 and region 3. Okay? So this is what is sometimes called an Einstein-Rosen bridge, and there are ways in which maybe I should mention this. I don't know if I'll come back to it later. But there's a way of interpreting this diagram, in which it looks like there are two disconnected asymptotic regions as a wormhole between two regions. And this is something that I think was first done by Wheeler. So I'm not going to spend too much time on this, but let me just mention. This I can erase, I guess. What you can do is you can try. What you can say is that here are two regions which look very, very, very distant, but there's an analogous solution in which what you have done is you've taken these regions and you have patched them together at some point very far away. And then what you get is a wormhole between, you can't, and then this region becomes a wormhole, between this part and this part. So you can take this region 1 and patch it to this region 3, and then region 2 becomes a wormhole between two distinct universes. Of course, the wormhole is not traversable. Okay? You can't actually jump in from region 1 and reach region 3. That's because there's no observer from here who can jump in and can reach this region. Similarly, there's no observer from region 3 who can jump in and reach region 1. But there are observers from region 1 and region 3 who can jump in and who can meet. So there's an observer from this region who can jump in, and an observer from here who can jump in, and these observers can meet in the middle. So it's clearer than this diagram. You can have an observer from here, an observer from here who can jump in and who can meet. So even though it looks like they're distinct universes, they can jump in and they can meet. So one way to think about this is that it could be that there's a black hole in front of you and there's a horizon, and you jump into the horizon, and there's somebody who's sitting in some extremely, extremely distant part of what these wormhole solutions are really telling you is that you could have a black hole sitting, so you have some observer here, he sees some black hole here, so he jumps into the black hole. And there's somebody sitting in an extremely distant galaxy, okay, and that person also jumps into the black hole that they see, okay, and it so happens that both of you meet in the interior. Even though these two black holes look like they're spatially separated by a huge distance, their interiors are identified in a way, like in this setup. Of course, very soon after you meet, both of you fall into a singularity, and that's the end. But it's possible, to have these wormholes that allow observers in very distant regions of space to get together and meet. Okay? So sometimes you will hear about these wormhole solutions, and what these wormhole solutions basically are is the maximally extended Schwarzschild solution But in a setup where you have identified some very distant part of region 1 with a distant part of region 3, which I've drawn in a cartoon here. This is just a cartoon. Okay? And what that means is that you have two people in extremely distant, distant parts of space. They both see a black hole. It looks to them like these are distinct black holes, but they jump in and the interiors of the black hole are identified. So they meet the interiors. Okay? So this is what's called.
We are not only extremely distant, they are causally disconnected. Right?
What is this? That's it. So 1 and 3 in this setup are, well, this wormhole solution is a setup where you take 1 and 3 to be, in some sense, topologically, part of the same manifold. So they're topologically connected. So you could imagine this. What you can do is you can try and use this solution to inspire another solution where you have one space-time, and you have two very distinct parts of the space-time. You have two black holes. So you have two locally black hole solutions, each of which locally look like they're Schwarzschild, but their interiors are identified. So the fact that this maximally extended Schwarzschild solution exists tells you that there's another solution you can write down in a single, in what is topologically a single copy of R4, which has the property that it looks like there are two distinct black holes, but the interiors are identified. So this wormhole solution is that, and you can see that the wormhole solution has to work because what you're doing is you're taking a very distinct part of region 1, very distant part of region 3, and you're identifying it, and that doesn't have any influence on the local physics. So this continues to be a solution locally. This continues to be a solution locally, but you've changed the global topology. So the wormhole is the same as the maximally extended Schwarzschild solution, but with a different topology.
So, but still there is no way that information can be transferred from region 1 to region 3.
No, there's no way information can be transferred from region 1 to region 3, but observers in region 1 and region 3 can actually communicate, can fall in and communicate. So if you really wanted to meet your friend on the other side of the universe, and you didn't have time, there's a cosmological horizon that separates you. You can both jump into the horizon and meet for some short time before you.
Also, while on this, in the Causal paper that you mentioned,
right.
In the last line, Causal says that this growth of the wormhole presents fundamental issues of principle.
I don't know. I don't know those fundamental. I mean, it's an old paper, so yeah. Now we understand that. I don't know what those fundamental. I don't know what those. I mean, does he elaborate on what that is? I don't remember.
That's a single line.
Okay, so I don't know.
But,
yeah.
this region 1 and region 2 and region 3, sorry, those must be separated by the cosmological horizon because they are completely causally disconnected.
No, but as you can see, someone from here can jump in and kill you.
But they are, both of them are causally disconnected. Right? According to the regions, they are causally.
If you have someone who lives only in region 1 and someone who lives only in region 3, there's no way someone in region 1 can send a message to region 3. That's what it means. If you have a world line of someone who lives entirely in region 1, world line of someone who lives entirely in region 2, then there's no way that these people can communicate with each other.
So,
but if both of them decide to jump in, then they can.
So, when you are...
if they decide to jump in early enough, yeah.
When we are thinking of the entire universe, suppose one part of the universe has an observer who is residing in the region 1, and another part has an observer who is residing in the region 3. And those two parts of the universe must be separated, must be causally disconnected. Separated by the cosmological horizon.
No, cosmological horizons work slightly differently here. The way the cosmological horizon works is the cosmological horizons are labeled by a point in the singularity. So this is one cosmological patch, for example. There's a cosmological patch that includes this, but the cosmological patch that includes this starts with at time like infinity here. So there's one cosmological patch here. But there are some cosmological patches that include part of region 1 and include part of region 2. You have to be, when you say cosmological patch, what you're talking about is always some point at which all geodesics terminate, and then the causal past of that. Okay? So here's a cosmological patch. This is the let me draw it in red. Cosmological patches are given by their endpoints, by their future endpoints. This is one cosmological patch. This is an example of a cosmological patch in this horizon. This includes some part of region 1 and some part of region 3. Now there is one cosmological patch that includes only region 1 and region 4. That's this patch. This patch includes only region 1 and region 4 and doesn't include region 3. What this patch refers to is an observer who has lived all his life in region 1. Such an observer is never influenced by anything outside this patch, which is somewhere in region 3. There's another cosmological patch that includes only, there's too many cosmological patches on the horizon, but there's another cosmological patch that includes only region 3 and region 4. Here's one cosmological patch which includes part of region 2, part of region 1, part of region 3, and all of region 4. And in this cosmological patch, you know, observers here, observers. So it's not the case that, you know, observers in region 1 can never meet observers in region 3. They can. You can see explicitly they can if they jump in. So you can see from this diagram. If you have somebody here and somebody here, they can both, you know, follow time-like trajectories and meet here. So is this clear? It's very simple. Just look at this diagram. You have an observer here, an observer here. They can both jump into this part in the future. They can meet. Okay. Yeah.
If you have two black holes, the basic assumption of spherical symmetry breaks down.
That's correct. So it's not exactly the solution. You have to write down a more complicated solution. But you see, because these things are so distant, what you do is you write down two solutions and then you identify the interior. So it's almost like a topological thing that you're changing. If you make these things distant enough, the effect of one black hole on the other becomes negligibly small.
Sir, sorry, I was absent in the last class. What is meant by jumping?
By jumping, it just means, just means jump in. Just means go in. There's nothing, I didn't discuss this in the last class. It's just the statement is just that you go into one horizon and somebody else, just a word line which enters the horizon from one side and the other side. It's not a technical word. Totally not technical. Okay, sorry, any other questions? Okay, good. So now I want to go on to talk about realistic collapse of black holes. Have any of you studied the collapse of black holes starting with a star, with a ball of dust? Have any of you seen the Oppenheimer-Schneider solution? Okay, so maybe one or two. But okay, fine. So I'm now going to describe to you, what happens if you take a ball of dust and you let it collapse. You see, because in this setup we have the Schwarzschild black hole solution, and this you can think of also as the eternal Schwarzschild black hole solution, because it's existed forever and it continues to exist forever. Now this is not how we expect black holes to form in our universe. We expect black holes to form starting with some star or some ball of dust that then collapses and forms a black hole. So you do expect that the late time geometry in some sense will look like these geometries we've been drawing, but you don't expect that the geometry at all times will look like the geometry of this kind. Now the first thing when you try and describe this collapse is you have to think of what's the appropriate coordinate system in which you can describe this collapse. Before I say that, there are many collapsing solutions that are known. I think the first solution that may have been discovered, maybe even before Oppenheimer and Schneider, may be the Vaidya solution. I'm a little confused about the history, but I should check up the history. But it was actually Vaidya who wrote down this solution, which actually involves just a null shell which is collapsing. And there are other kinds of collapse solutions you can write down, including collapses of thin shells, which are all simple. The Oppenheimer-Schneider solution is different from the Vaidya solution in that it doesn't involve a very thin shell of matter collapsing, but rather a dust, a ball of dust which is collapsing, and therefore it in some sense is more realistic to what a star is doing. But often when you consider collapse situations, nowadays it's often more convenient to just think of thin shells collapsing because they capture all the essence of that. And so the Vaidya solution in some sense is perhaps more important than the Oppenheimer-Schneider solution. The reason I'm not discussing it is because the discussion of thin shells requires these things called junction conditions across these thin shells, and I didn't want to go into that. So I'll discuss this solution, which is technically simpler and in some sense models more closely what happens to a star, but there are these other solutions, including the Vaidya solution, which are very important and very useful to look at. Okay, so now I want to describe the collapse of this shell of dust, and we know that outside the shell the metric has to look like the Schwarzschild metric. The question is, what does the metric look like inside the shell? Now it actually is a bad idea to try and use Schwarzschild coordinates for the whole setup, because we've already seen the Schwarzschild coordinates become bad past the event horizon, and therefore you want some better set of coordinates to describe the setup. And one good set of coordinates to describe at least the interior of the shell is what are called co-moving coordinates, which involve the following, in which you say that, so what's the picture? The picture is you have some shell, okay, of dust, and it becomes smaller, and then it becomes a black hole. Okay, so you have some big shell of dust, and these are snapshots in time of what this is doing. And what this looks like in terms of in a space-time diagram is, of course, that you have a shell of dust. Time. you have a shell of dust, and the shell of dust is collapsing. Your shell of dust, first it goes from, I've drawn minus r to make it look more realistic. So here's r, it starts with some finite value of r, and then collapses. Okay. Now it's useful to think of a pressure-less ball of dust, which is a situation where the rest energy totally dominates over the kinetic energy. So this is what happens when you consider dust, for those of you who've seen cosmology, where the pressure is negligible compared to the rest energy density. So I'm going to consider a setup here where the pressure of this dust is 0. And therefore you can think of layers in the shell, layers of matter in the shell, and they follow some world line. For example, this is a world line of the outside of the shell. And there may be another particle that's sitting here, and that particle follows some world line of this kind. Okay. So there may be another particle that's sitting here that follows some world line of this kind, and similarly. Okay, so there are all these particles that follow these world lines. And one useful coordinate system to use is to use the proper time as measured by a clock sitting here, okay, to be the time coordinate. In fact, you can also use the proper time of observers who are outside the shell. You can even use this proper time coordinate for things which are outside the shell, which just reflects the proper time of an observer who is a little bit outside the shell and is in free fall, is following the same geodesy. So you can use this proper time coordinate to try and describe how the shell falls. And what that means more precisely is that you write the metric as a spherically symmetric metric, but in the following coordinate system. The statement is you write the metric as ds squared is minus d tau squared, okay, plus some a into dr squared plus d into d omega squared. Okay, where a is of course a function of a of tau r and d is a function of d of tau r. Okay, but I won't write this dependence. It's understood that a is a function of a of tau r and d is a function of d of tau r. This is again a metric that has spherical symmetry. But it's a different choice of coordinate system from the one we made yesterday. And these A's and B's, by the way, are not related to the A's and B's I wrote yesterday. They're just some other A's and B's. And then you can easily check that you can put coordinate systems in this form as well as we did yesterday. We put them in a different form. But anyway, what I've done here is I've chosen this coefficient to be -1 and these to be some arbitrary A and B. And this is a general metric. And physically what this corresponds to is an observer who's sitting on the surface of the star and measuring time by that person's proper time. Okay, now the interesting thing that we are going to do is, and the advantage of this is that we can take a stress tensor which has the property that the only non-zero components are t tau tau, and that is some rho naught. And all the other components of the stress tensor are 0. This is a statement that your observers are moving along this. If you look at balls of this dust, their velocity is along d by d tau. Their velocity is only along tau. They're basically in this coordinate system, they're sitting at a constant value of r. In this coordinate system, where r is measured by what happens to the trajectory of world lines, they're sitting at a constant value of r. And you know that you can write. So maybe this we can do in the tutorials. You can check that if you have something which is just sitting at rest, then the only non-zero component of the stress tensor is the t00 component, right? In that coordinate system, there is no tij component. That's because these things are not moving, and there's no pressure. So the only non-zero component is the t00 component, and that's rho 0, some rho naught, which we'll specify in a minute. But there's some non-zero zero, actually some rho. Sorry, not rho naught. Rho naught is the initial value. It's some rho, and everything else is 0. Okay, so we want to find a solution with this metric and with this stress tensor. Okay, so is the problem clear? This is the problem. I'm going to show you it's not so hard to find an exact solution. Okay, good. So now, the main thing is to use this and is to find the components of the Einstein tensor, is to use this coordinate system and to find the components of the Einstein tensor. I won't do that. Yesterday, I think in the tutorials, maybe we discussed using these programs to find components of the Einstein tensor given a certain coordinate system. But it's a completely mechanical thing to do. Given this metric, you can find what G nu is. So let me just write down the result for G tau R. differentiation with R, and dot means differentiation with tau. Sorry, and I have missed some facts divided by. So this is g tau R, which you can work out. The thing is that g tau R has to be 0, right? Because the Einstein's equations are telling you that g mu nu is 8 pi t mu nu, and there's no t tau R component. Right? So you want to set g tau R to 0, and you can check that one solution to this involves the following. Sorry, is there a question about this? So one specific, actually, the one solution to this is A is equal to B prime, like E into N of R, or let me call it something, X of R, okay? For convenience, so you can check that this is a solution basically by showing that makes this vanish, and the way you can make sure it makes things vanish is that you can check that A dot twice B prime, B dot prime by B into R minus B prime squared B dot by B squared R. And then you can check by substituting this that A, that combination vanishes. So just use this formula for A dot and substitute it there, and you can check that will make things. Okay. Any case, so this is the solution. Oh, sorry, I'm writing F here again. Thanks. Okay, but now we're going to make a particular choice for X, which is the same choice that Oppenheimer and Schneider made, and which actually will already give a solution. You can check. You can use more general choices for this X of R. The solution allows you to have other values of X of R. We're going to choose X of R is equal to 4. It's a choice which makes some coefficients drop out. There's no reason you have to choose X of R equal to 4. Okay, so I encourage you to try to work out the other solutions that you get if you take X of R equal to 1 or X of R equal to some other function of R. But the point is that you take, this is a particularly convenient choice because it's chosen with some hindsight to make some things become simple. Okay. Okay. So let's say we do this. So then what happens is that the other components of the Einstein tensor with this choice become simple. They become, let's work out GRR becomes B prime squared B dot minus 4 B double dot. So this is what GRR becomes. There's no A anymore, right? Because A I already said to be something in terms of B. So now the only thing that I have left is this is B, and this is what GRR is in terms of that. Okay, and you can check that what this requires is the following setup. It requires B dot. Right? If you want to set GRR equal to 0, then GRR also has to be 0 because there's no TRR component. So if you set GRR equal to 0, then you see that you get B dot is equal to some B to the 1/4 into some Y of R, and that implies that if you integrate this once more, is that B to the 3/4 is equal to F of R tau plus G of R. So I'm just integrating the Einstein equations and I'm getting this. Is this clear so far? Are there any questions about this? Can you all see this? By the way, I do have these notes and I can put them up on some website if you want to look at them. But anyway, is these things clear? Are there any questions about what we are doing or any confusion about where we are heading? Okay. Okay. I don't know if this means everyone is understanding or people are getting lost. So just to say, there's nothing complicated I'm doing here. What I did is I started with this metric. There's a physical reason to start with this metric. It involves a choice of co-moving coordinates. In this metric, we say that the only non-zero component of the stress tensor is the tau component. Okay. So we are looking for a solution that has this property. Then you compute the Einstein tensor. It's a completely mechanical computation. You get some answer. Using this, you can find you can solve for A in terms of B. There's a general solution, which is, A is given by this, B prime square by B into x of r. Then we made a specific choice, which is x of r equal to 4. This choice, there's no reason for you to like this choice right now, but I'm saying that it will make things a little easier in hindsight. But it's not a unique choice. You can make other things and find more general solutions. We only want to find one solution, so we chose x of r equal to 4. With this choice, you get this for the GRR component. That's this term. Okay? And you can integrate this, and when you integrate this, you get that b to the 3 by 4 has to have this form. If that happens, then GRR vanishes. Okay, that's b dot minus 4b into b double dot vanishes. Okay. Now, if this is, you can check that this choice of b also sets g theta theta and g phi phi equal to 0. In this particular case, you choose b to be this, and you also get the g theta theta and g phi phi. Okay. So the only non-zero component we have now is the g tau tau component. And we have now, we had one function b which was a function of r and tau. Remember, this function b was a function of tau and r. But we have reduced that freedom a lot, and we've made it only a linear function in tau, multiplied with two functions that are functions only of r. Okay? So that's what is going to allow us to solve this. The fact that we now once again will get an ordinary differential equation. Now the difficult part of solving the Einstein equations is that you get partial differential equations, which are functions of tau and r. By doing this, we have, by making some clever choices, we have reduced everything. We have solved the tau dependence completely. And we have only these functions f and g that we now need to solve for in terms of the initial density. Okay. So now we can work out what g tau tau is, and it turns out that g tau tau this was some, sorry, if you have b dot is equal to b to the 1 by 4 into some function of r, then you integrate that. Okay? So it tells you that, db by this is equal to y of r into d tau. Actually, y here may be the same as f. So this y may be the same as this f. Maybe there's a factor of 1 by 4 or something, which you just integrate this. So it's just db by b to the 1 by 4. Y of r.
I couldn't see the dot on the left hand side.
Yes, and then you integrate this, you get, then you get b to the 3 by 4 is this. This is probably, this f is related to this y by some factor of 3 by 4. Is that it? Here? Very good. Okay. So now we work out what g tau tau is. Tau tau has the following form. In terms of this function f, 4f f prime by e into tau f plus tau f prime. Okay, I'm writing down these components, but I strongly encourage you to try and work these things out. They're just mechanical calculations. Okay. Now I want you to notice that we have written things as functions of r, but in fact we have some more freedom. And the additional freedom we have is the fact that r we didn't specify in the beginning. You see, I wrote things as d of tau plus a into dr squared plus b into d omega squared. If I now make some coordinate transformation which is purely a function of r, in which I define the new coordinate r prime as some function of the old coordinate r, but not involving p, that will preserve this form. Right? So even though I specified this coordinate system, I still have some additional freedom, which is to redefine r in terms of the old r coordinate. So I can define a new r coordinate which is only a function of the old r coordinate, And that will completely preserve this form. And we can actually use that to get rid of this function g. Now we can use that to get rid of this function g, and to see what a convenient, to see what a convenient choice would be. It's useful to write down what the metric is. Okay, so the metric in terms of all these things, with whatever we have done so far, which is not the full solution, looks like this. Looks like, actually, let me just write A and B. Already has the metric on top, so I'll just write A and B. So if you just go back and, we had some series of transformations, this is B, B is f of r tau plus g of r, A is b prime squared by b to 4, which was x of r is equal to 4, so it's 4b. So in any case, if you go back from these transformations, you will find that A and B have the following form. That A looks like 4 by 9 tau f prime r squared by tau. C. Okay. And B B is obvious, it comes from here. That's because B to the 3 by 4 was this, so B is just that to the power 4 by 3. Okay? So you see that that's what? That's not A dot, it's A is equal. This is something on the board, it's not something else. A is equal to 4 by 9 into tau f prime of r plus g prime of r squared by tau f of r plus g of r to the power 2 by 3. Yeah. What f? A double prime? Which f?
G tau tau. The form of G tau tau.
This? No, this is f single prime. Okay. So this is the form for B and for A. And now you see that there's a convenient choice you can make. Yeah.
How do you call this A and B?
By going back, you see this is B and this is A in terms of B.
But how the choice of R prime that we have got?
So far I haven't made any choice of R.
Which was dependent upon R.
So far I have not made that choice. I'm motivating the choice. I'm going to make it now. Okay. So now you have the solution. And the question is, what is a good choice to choose for G of R? You see, let's think of the solution at tau equal to 0. Okay, so which is some initial, arbitrarily chosen initial point. If you choose a solution at tau equal to 0, you see what you're getting here is G r to the power 4 by 3. Okay? So B looks like G of r to the power 4 by 3 at tau equal to 0. Okay? So that, one convenient choice is to choose G equal to r to the power 3 by 2. In which case at tau equal to 0, it would look like r squared d omega squared. So there's a convenient choice of the new coordinate you can make, okay, which here I'll just write by saying you choose G of r equal to r to the power 3 by 2. Okay? And the reason you can set G of r and not have to solve for G of r is because you have a freedom to redefine the coordinate r. So you choose the coordinate r so that G of r is r to the 3 by 2. Is this clear? Okay. So you've chosen G of r as r to the 3 by 2. And if you do that, then you see that your solution will simplify quite a lot. In fact, it will look at tau equal to 0, these 4 by 9 factors will also cancel out. And at tau equal to 0, it will look like minus d tau squared plus dr squared. A will just become 1 at tau equal to 0. Okay? The reason it will become 1 is because you chose G of r as r to the 3 by 2. So when you differentiate it, you get some factor of 3 by 2 squared which completely cancels off this 4 by 9. And there's some factor here which totally, you'll see A will just become 1 at tau equal to 0. And B will become r squared. Okay. So with these choices, we see that this means that if you look at the length element restricted to tau equal to 0, restricted to this surface, hypersurface with tau equal to 0, that just becomes dr square plus r square d omega square. So that's the significance of this choice, which is dr is r to the 3 by 2. It tells you that this length element becomes dr square plus r square d omega. Okay, but now we still have the function f, which we have not solved, and we don't have any more freedom left. So we have to determine what the function f is. Okay, so the function f is where the dynamic comes in. But to determine the function f, we first have to specify, what rho is initially. Okay? Now it's important, and this is an important fact about the Einstein equations, is that you can't specify rho for, you can't specify rho for all times. What you can do is you can say, I start with some initial density profile. Okay. I start with some initial density, and you can tell me the time derivative of the density. I start with some initial metric on that hypersurface. That metric and that density also have to satisfy certain constraints, which are called the Hamiltonian constraints, which correspond to some components of the Einstein equation. And after that, the evolution is totally fixed by the equations of motion and the fact that the stress tensor is conserved. So this is a general feature of the Einstein equations, which is that their structure is as follows. Now you are allowed to initially specify some metric and a time derivative of the metric, and specify some initial matter distribution and a time derivative of the matter distribution. These things can't be totally independent, this initial data. It is subject to certain constraints called the Hamiltonian constraints, which correspond to certain components of the Einstein equations. After that, you let things evolve, and then the equations determine everything. They determine how the matter evolves, and they determine how the metric evolves. Okay? So in this case, what I'm going to do is I'm going to specify. Just to tell you how the structure works in this case, what I'm going to do is I'm going to specify the initial density profile at tau equal to 0. Once I've specified the initial density profile at tau equal to 0, then with all these coordinate choices, I don't have any additional freedom in specifying the initial, then that tells me how the function f has to look. Okay? And it tells me how the function f has to look, which comes in a sense from the constraints. And then after that, the evolution of everything is totally fixed. Then there's no freedom in the evolution. Here or some
It rings every day twice.
It what?
Rings twice in every class.
This is a bell.
Yeah.
From the class.
See, this
This
is
is the clock.
the bell. There are other classes going on, right?
Oh, I see.
The time is from
I see.
12 to 12:50.
Okay, fine. I was worried it was feedback.
No.
Okay. Okay. The initial density profile we will specify. By the way, if this issue of the Einstein equations and their structure, I think also we can do in the tutorials. We can discuss, right? So far I haven't said too much. We can do in the tutorials, but a couple of things which would be useful would be to check these components and also to look at this general structure of the Einstein equations and how you specify the initial data and how you evolve things. This is something which is very useful to understand. What the structure of these partial differential equations is, and if you haven't seen it before, you should certainly discuss it in the tutorials. What I'm going to do now is I'm going to specify the initial density distribution. The initial density distribution I'm going to use is going to be a distribution which is going to say that there's some density in the star, and that's it. Okay, there's some star, and everything outside is vacuum. So what I'm going to say is I'm going to say that you look at rho at tau equal to 0. Where Rs is some number which I can pick, tells me the initial extent of the star, and this is equal to 0. R is greater than Rs. And then, so now we've specified everything, and we need to solve g tau tau equal to 8 pi tau tau. Okay. Where I wrote g tau tau. But anyway, this equation becomes something very simple. It becomes the equation it becomes the equation 8 by 9 ff9 by r squared is equal to 8 pi rho naught. Yes. solution, which is the first, which is f is equal to. Now there's a choice making of the square root. You know, when you solve this equation, you will get a square. Okay, this is the derivative of f squared. Okay, so when you do that, there's a choice of square. There's a choice of sign you have to make, and you find that f is minus 6 pi rho naught r cube. The reason for choosing this sign is that it corresponds to a shell that's collapsing rather than a shell that's exploding. If you were to use the opposite sign, which is a sign that's with a plus sign, okay, that would give you what we discussed yesterday was a white hole solution. Was a shell that starts with infinite density and then that explodes outwards. Okay? So that is also a solution of the equations of motion, but it's not a solution that starts with smooth initial data. It's a solution that starts with a singularity and becomes regular, and it's a white hole solution. This negative sign makes sure that it's a black hole solution you're considering and not a white hole solution. There's some additional constant which I set to 0 here, which again, because we're looking at a particular solution, you can check that there's a constant of integration here which I just set to 0. And in any case, once you have done this, then we have a metric which I'll write down now. This completely solves now the equations, and the final metric that you get is as follows. Okay, so there are two parts to the metric. One of them is for r smaller than rs and the other is for r greater than rs. For r smaller than rs, it looks like ds squared is minus d tau squared 1 minus into 1 minus root of 6 pi rho naught tau to the power 4 by 3 into dr squared plus r squared there's a minus 1 here on top of the bracket. Okay, so this is divided, no, not divided by this one. Okay. This is the full solution for r smaller than rs. And another part which tells you the solution for r larger than rs. We are coming to the end of our long algebraic manipulations in a second. So this is true for r larger than rs, and this is true for r smaller than rs. Okay, so the metric has two parts. There is a part for r smaller than rs and a part for r larger than rs. And in both cases, we have a metric, we have a stress tensor, and we have a metric and we have a stress tensor. Notice, now actually this is the end of all our manipulations. We have a solution now. Notice that in this solution, what we specified was rho 0, which was the initial, profile of the density. After that, rho of t is totally specified. Okay, this is rho of t. It's rho 0, and then the density increases monotonically in this way with tau. And we don't have any freedom to specify rho of t, and that's because once you specified rho of 0, then after that the fluid evolves under its own, basically under the fluid equations of motion, using the fact that the stress tensor is conserved. And that gives you the fluid equations of motion. So once you specify the initial fluid, then it completely determines how the fluid evolves. The fact that we, at some point we made this choice between A and B, we put this factor of 4, restricts actually the initial velocity you can give to the fluid. Okay. So here you see that there's the initial velocity you can give is totally fixed. Okay. How you can the first derivative of this velocity is totally fixed. In general, by allowing more general relationships between A and R, at some point I made this choice of 4. You can allow for more general velocity profiles of the fluid in the beginning. But in any case, that's not something which is of interest. This solution is good enough for us. And we see that you specified rho naught, and then you specified rho of t, and you have this metric, and you have this metric for R larger than Rs. Okay, now here's an important tutorial question. We proved yesterday Wormhole's theorem that told us that for t mu nu equal to 0, there was a unique spherically symmetric vacuum equation of Einstein's equations. Vacuum solution of Einstein's equations. This is a vacuum solution, but it doesn't look like the Schwarzschild solution we wrote down yesterday. Okay, so I would like you to do. Actually, you don't even have to check very explicitly. That may be a little hard, but I want you to do the following in the tutorial. Determine n. So you can rewrite this metric, of course, in terms of the Schwarzschild metric. That's a theorem we proved yesterday. That metric is a one-parameter family of metrics which has a parameter n. Okay, I want you to determine what m is in terms of these parameters here, which are rho naught and Rs. So that's let me see how much. Okay, so why don't you think of how you can do it? The answer is simple. But basically, trying to find the full coordinate transformation is a little hard. If you think about it a little, you might see a shortcut to try and determine the mass in terms of rho naught and Rs, but you can determine the mass in terms of rho naught and Rs. Okay? Okay. In fact, later on, I'll give you another way in which you can determine the mass. Okay. Okay. So now we are interested in the physics of the solution. We have the solution, and we are interested in understanding what it means. Now the first thing to recognize is that we chose some R coordinate. Okay? But this R coordinate in this setup, lines of constant R, as we said, corresponding to an observer who was falling, corresponding to some co-moving observer. So somebody who's sitting at constant R and omega in this setup is what in another more intuitive reference frame would be somebody who's actually who's collapsing. Okay? So somebody who's sitting on the surface of the star, which is R equal to Rs here, corresponds to constant R in these coordinates. So there's a more there's another R which corresponds more intuitively to what our notion of radius is, which is what we used yesterday, which corresponds to looking at the radius of the S2. And so it makes much more sense to think of the physics in terms of the radius of the S2. Okay? So when you do that, you see what's happening here. You look at this solution. See that the radius of the S2 is given by 1 minus root of 6 pi rho naught into tau raised to some power 4 by 3. The power 4 by 3 is not important. But the fact is that this is something that starts, with some, if you sit at any point in constant R inside the sphere, you can start at any value of R as long as R is smaller than Rs. And what happens is that the radius of the S2 shrinks and it goes to 0 in a finite time. So in some time, this radius of this S2 just shrinks and it goes off to 0. I think it's right. Okay. Okay. So you sit here then and your radius goes off to 0, and the same is true here. Okay. So really the way to think of these metric components, to think of the solution is as follows: is to think of the diagram we were making just earlier, which is that you have some initial profile of density. This is Rs. Let me draw it from one side. Rs. This Rs goes off to 0 here. So there is some shell of dust, and it collapses, and then it becomes some singular thing. Okay? So this is the solution that we have found. This is the solution that we expected, and this is the solution we have found. This is the origin of polar coordinates, 0. And you see that you started off with some shell to some extent, and you have, you've made it collapse, and now it's collapsed down to singularity. And the reason you can see that this is the solution we found is because you can measure the radius of the sphere at Rs. You can ask, what is the size, what is the circumference of the sphere at Rs? That's a measure of, the proper distance at Rs. That's really what we mean by when we talk about the radius at a point. The distance from the origin, what we're talking about is you look at the S2 at that point and you look at the circumference of that, and you can see that that goes off to 0. It goes off to 0 linearly. Therefore, you can see that, what this Rs is doing is it's going down to 0 in this. So is it clear how this solution, which looks, written in these coordinates, in some other coordinates where you're talking about, where you draw, where you draw the radial direction in terms of the radius of S2, looks like this. So in these coordinates, somebody who's sitting at R can just continue to sit at R. R equal to constant, you can just evolve with E tau. And you might think you're sitting at R equals constant, but you're not really, because what you're calling R equals constant is a point where the circumference of the sphere is shrinking constantly. So what you're thinking is R equal to constant is actually something which is, which is collapsing. And you can see that from the stress tensor. This density is going off to infinity. So you can see that, you think you're sitting at R equals constant, but it's not true that nothing is happening. Things are happening. The radius of the sphere is shrinking, and the stress density is going off to infinity, and it's a collapsing solution. Is this clear?
So when we wrote this two solutions,
Yes.
these two solutions for R less than Rs, R greater than R.
Yes.
This is the Rs at tau is equal to 0.
Rs is just a parameter. So this is not in these coordinate systems, Rs is a constant. It does correspond to the physical radius at tau equals 0. At tau equals 0, the metric looks like dA square is minus dt square plus dr square plus r square d omega square. So this Rs corresponds to the physical radius at r equals 0. This Rs is always, demarcates the two different regions. But Rs equal to constant in these coordinates, this is the trajectory of Rs equal to constant. So in some physical coordinates where you're looking at the radius of the sphere, Rs equals constant would be something like this. But in these coordinate systems that we've chosen, Rs equal to constant is this point. So this is always the solution for R smaller than Rs and R larger than Rs. But except that Rs doesn't correspond to what you usually think of as the radial direction. That corresponds to what is the radius of the sphere.
Sir, sorry. For R greater than Rs, there should be no column.
For R greater than Rs, there should be no, that's not true. You see, in these coordinate systems, you can start at some point here, and you will still end up here. So it's a question of how you extend the. As I said, this coordinate system corresponds to an observer who's sitting outside and freely falling. Okay. So someone who's sitting here and just freely falling will also collapse. It's a question of what I told you what the coordinate system meant in the beginning was you were measuring things by terms of observers who are freely falling outside, okay, and you're measuring time by their clock. So if you have an observer who's sitting outside R equals to Rs, he also collapses because of the gravitational attraction of the star. So this observer also falls into R equals 0. That's why there's collapse even outside R equals Rs. It's collapsed because of the way you define time. You can go to some other coordinate system, which is the usual Schwarzschild coordinate system, and you can think of observers sitting at constant R there, and those observers are not hitting a singularity.
So what does it signify T tau tau equal to 0?
E tau tau equals 0 just means there's no stress tensor. So they're in a vacuum here. This is the vacuum. You can be in a vacuum, as in the Schwarzschild case, and you can still fall into the singularity. Schwarzschild solution is a totally vacuum solution. If you're some freely falling observer, you will fall into the singularity. Yeah.
So it seems that after a finite time, Rs is 0. But
Rs is not 0. Rs is always something which is, Rs is a coordinate time. So Rs doesn't become 0. Rs is a number. Rs doesn't become 0. What becomes 0 is the radius of the sphere. Rs is just a number. In these coordinate systems, this is R equal to Rs. This is still, even here, this is R equal to Rs. But what's happening is that at this point, the coordinate system that you're using is a very funny coordinate system, where what you're calling R doesn't correspond to the radius of the sphere. It corresponds to something else. You have to be careful about, in GR you always have to be careful about coordinate systems. R equal to Rs is a number. Rs is not a function of time. Rs is a constant.
So the radius of the sphere is a function of time.
The radius of the sphere is a function of time, which is decreasing.
Which becomes 0 after some finite
Correct.
time.
Correct.
But apparently from what you've drawn, it continues to be 0 after that.
Oh, good. So after tau equal to this point, of course, this solution becomes unreliable. This is not the solution you should use. After tau equals 0, this is hit a singularity. So you shouldn't trust a solution, beyond the point where the radius becomes 0. At that point, it becomes singular. So that's why, I drove. You'll get some imaginary solutions.
So RS is remaining constant throughout.
Yes.
Even though the trajectory is like this.
Yes.
So can we say that we are measuring RS in the co-moving frame? That is right.
RS is measured in terms of some coordinate distance which is measured by co-moving observer. So lines of constant R here correspond to trajectory of an observer who's just sitting on the surface of the star. RS is the surface of the star. So that observer thinks that nothing is happening in the world around him, but things are. He's just really falling, but something is happening. He's falling into a singularity. He thinks he's at constant R, but he's not at constant R as measured by the size of the sphere. So is this point clear? This is an important point. The coordinate system we have chosen. The coordinate system, just because we've written it as R doesn't mean it really is what we mean by R. Okay? We chose a coordinate system which was a useful coordinate system to describe things in. What we really physically mean by R is always the radius of the S2, and that is decreasing. Okay, so the coordinate R is not decreasing, but the radius of the S2 is decreasing. Okay, that's why I've drawn the figure here, and this is a coordinate system in which I've drawn the radial direction in terms of the size of the S2. Okay, let me say, yeah.
I am unclear about this thing that the metric, why is it time dependent?
Why is it time dependent? Because it's a collapsing situation.
But it is the Schwarzschild geometry with a coordinate transformation, right?
So that you can ask about that one.
So it is the Schwarzschild geometry with a with a coordinate transformation.
Correct.
So it is static.
Correct. So it is static. So you should do in the tutorial, you should ensure that it is static. Okay, static doesn't mean that there is no coordinate system in which I can write things in a time dependent way. You can take your world and write things in a time dependent way. Yeah, so it is static. This is a static geometry. But static doesn't mean that for any choice of time things look static. Static means that for a choice of time, it looks like all the metric components are independent of time, and there are no cross terms between T and X. That's what for a choice of time, not for all choices of time.
For our choice of time.
For a choice of time. Static just means that there exists a choice of time, whether or not it's your choice of time. There exists a choice of time for which the metric looks like dt squared plus some spatial part, where these metric components are not functions of E and there are no cross terms. Okay, but there exists a choice of time. There exists a choice of time in this geometry where this is true. That is not the choice of time we have chosen here. There is a transformation of coordinates from here into the static line.
But what about Barkov's theorem?
Barkov's theorem is correct. That's what I'm saying. There's a transformation of coordinates that takes us to the Schwarzschild geometry. That's what the tutorial question is. It's determine. I don't want you to determine the transformation of coordinates. By the way, the Oppenheimer-Snyder solution is also part of these APS-DR Centennial papers that I discussed yesterday. So you should look up the Oppenheimer-Snyder paper. It's called On Continued Gravitational Collapse. It's written in slightly different notation from this paper, from what I'm describing here. But it tells you also the choice of the explicit transformation from this to the Schwarzschild coordinates. But even without determining that full explicit transformation, which is a hard thing to do, you can determine what M is in these Schwarzschild coordinates. So you can determine, if you made the transformation, what the value of M should be. So you should be able to determine that without doing the full transformation. Very slowly. Okay.
Even the co-moving observer, don't he think that that is the density at R less than R always? Even he sees that the density is not great.
That's correct. The co-moving observer also sees the density is great. So co-moving observer doesn't realizes that things are happening. Bad things are about to happen to him. Tidal forces become large and so on. But he thinks he's sitting at constant R because that's how we defined R. I mean, that's the definition. So things are happening to the co-moving observer. Okay, good. So now do this transformation in the tutorial. Okay, so now we've got the physics of the solution. Now there is a useful thing which maybe that I will look at. Okay, here's a related question. Okay, consider surfaces of constant x. The x is this. consider lines of constant x, where x of r tau is the radius of the sphere, so that's r into root of that into power 2 by 3, okay? And show that m, where m is what you determine here, is null. Okay? So you show that x equal to 2m is actually null. Is the question clear? You consider lines of constant x. The x is this x. Is what appears in this factor here. Okay? So you can consider in this coordinate system lines of constant or trajectories of constant x. Sorry, just one second. Maybe I should use, just one second. No, this is not what I want to do. I want you to use the part outside. X is equal to r into this. Not the part inside, but the part outside. Yeah. So consider x, where x is this part, r into h of r tau to 2 by 3, which is also the size of the sphere, even for the outside solution, not for the inside solution, and show that at x equal to 2m, that this becomes null. Okay?
These are the transformations that will make it into torsion.
Yeah, but you don't have to determine the full transformations. In fact, here's a shortcut which will let you do it. Look at this lines of constant x at different values of x, and you can determine the value of x for which it becomes null. That also tells you x is, tells you what m is. So you don't have to do the full transformation. Similarly, for this, you don't have to do a full transformation. You just have to check if the transformation exists, which is easier than checking that you should do the full transformation. So actually, the shortest way may be to start with this. Consider lines of constant x and find the value of x for which things become null. That value of x corresponds to 2. So that actually will let you answer this also. So maybe if you have only a few hours, here's a simple way to do this. Look at lines of constant x, determine the value of x for which this line becomes null. Okay. X equal to constant becomes something null, and x equal to constant, and of course omega equal to constant. So just motion in r and tau while keeping x constant. Find when that becomes null, and that will give you. Okay. So in this, what does this correspond to? You see, what this corresponds to is that there's some x here. This is 2m. And this is actually a null surface. Okay? So what's happening to light rays? Even light rays, there's some light rays which go off from here and which go off. Okay, so let me draw light rays in green. If RS is much larger than x to start with, okay, then it looks like initially you're in flat space. Okay, so light rays just go off. But as you maybe that looks like that. You take light rays in the beginning. But as you come closer and closer to here, when you look at light rays that are emerging from here, these light rays basically get trapped at x equal to 2m. Okay? So if you look at the trajectory of light rays here, these light rays get trapped like this, and they start going up at constant r in these they start going at constant x in these coordinates. That's because if you think of a light ray at the horizon, it basically lives at the horizon. It can't get out. So it gets out very slowly. You think of a light ray here, it gets out very slowly. So light rays which are closer and closer to the horizon, they get out they don't start quite at x equals to 2m. Slightly outside, and they get out very, very slowly. And of course, a light ray that starts inside, can't get out at all. If you take a light ray from here, that light ray goes here. So if you think of the trajectory of light rays starting at different values of x, what I've plotted here is in terms of the radius of the sphere. Then you see that these light rays, light rays with very large values of x behave a lot like light rays in flat space. But light rays around, this point, which is the event horizon, stay stuck at this point for a very long time, and then they emerge after a long time. And light rays which are inside eventually fall into the singularity. They can't emerge outside at all. So is this clear? This behavior of how light rays behave?
Why do they emerge after a long time?
These ones?
Yes.
They climb out slowly, and after some time, once they get to larger and larger values of x, they are less affected by the gravitational interaction. And so it's easier and easier for them to climb out. Okay, so here's how the Penrose diagram of this solution is drawn. And this is a realistic Penrose diagram. start at fast time like infinity. This white part is the shell. RS. This should be just the start. This is the horizon. This is the Penrose diagram on the realistic side. It's basically the same thing as what we have drawn here, but drawn in coordinates where light rays go at 45 degrees. So this is the line of constant x, but because it's a light ray, because it's become null at x equal to 2m, I've drawn it as 45 degrees. And it's basically the same diagram, but with the coordinate transformation to make light rays go at 45 degrees. So you can see there's some shell of the star, and that collapses in some way, but you get this horizon, which shields the singularity from the rest of the space, and the horizon is defined as usual as a point beyond which things can't escape. So the horizon here is at x equal to 2n, and beyond that light rays can escape. So if you have a light ray that starts from here, it spends a long time and it reaches, eventually it gets out. If you have a light ray that's very far here, you're in some region which is very far away from this, things look a lot like they're in flat space. So this is a Penrose diagram, but now a Penrose diagram of collapse, and you can see that you can see that there's no region 2, 3 and 4 here. These other regions which we had in the maximally extended spot shell solution don't actually exist here when you form something from collapse. Okay? So those regions were artificial because they corresponded to an eternal black hole, which in some sense emerged from a white hole and fell back into a black hole. And in this more realistic collapse, these things don't exist. Okay, so are there any questions about this?
Sir?
Yeah.
Inside this R equal to 2a, what does the Schwarzschild metric look like?
Inside R equal to, it's a question of whether you're inside R equal to RS or R equal to 2m. If you're inside R equal to 2, if you're inside R equal to RS, then there's a difference, there's something else because you're not in a vacuum solution. Once you're in the vacuum solution, then the Schwarzschild metric looks the same. It just depends on one parameter. Okay, so now how many of you have seen the Kerr and the Royston-Ostrom black holes? You have only 4, so not all of you. Okay, then I have about 5 minutes left. Let me describe to you some other solutions. Okay, so this is a collapsing solution. Now, just for the sake of completeness, I'm going to describe to you some other solutions. But again, in the language that we used yesterday, where I'll write down an eternal solution, not a solution which is formed from collapse. In fact, for a lot of so basically there are two things that we can do to this Schwarzschild solution. We can add charge to it, or we can add angular momentum to it. And there isn't anything else that we can do, and that's the fact that there isn't anything else we can do is what's called the no-hair theorem, which I'll now probably discuss tomorrow. But basically you can take a black hole and you can throw charge into it, or you can spin up the black hole. And these two solutions are called, the Royston-Ostrom and the Kerr solution respectively. In fact, it's not so easy to come up with, exact solutions of collapse that collapse into, into these Kerr black holes. I think for Royston-Ostrom black hole you can do this. But for things, if you want to come up with an exact analytical solution, that's very hard to do. So instead of going into the technicalities of trying to describe how these things come from collapse, I'll just write down some solutions which correspond to the Royston-Ostrom and Kerr solutions, and then we'll discuss their properties tomorrow. Okay, so here is what's called the Royston-Ostrom solution, which looks a lot like the Schwarzschild solution. It's again spherically symmetric, and it has a charge that looks like E squared by 2. So do you know why I'm allowed to have the solution even though it's spherically symmetric, and why it doesn't have to be the Schwarzschild solution? This is a charged black hole. And clearly this is a metric for a charged black hole. If you take the electric field for this metric and you integrate it, you find that the charge is this E. Okay. Do you know why I'm allowed to have this?
It's not a vacuum solution.
That's right. It's not a vacuum solution, because there's an electric field. The electric field has some energy density, so it's not a vacuum solution. So you can check if you write down, the Maxwell stress, the stress tensor for the Maxwell field, that this satisfies, the equations of motion for the stress tensor corresponding to the Maxwell field with a charge at the origin, which is of size E, so it's not a vacuum solution. This solution also has horizons. Okay? These horizons occur when okay, and this has solutions which are R is equal to M plus or minus square root of n squared minus e squared. Okay. So that's one solution, as E is very small, as you take E to 0, you see one of these solutions goes to 2m, the other solution goes to 0. The real solution, the solution with m plus m minus m square minus e square is called the R plus is called the outer horizon. R minus is called the inner horizon. This is actually an unphysical region in realistic things that are formed from collapse. So in fact this, what really the horizon is this outer horizon. This inner horizon is something that exists in this exact Rice-Nostrom metric. But if you look at things that are formed from collapse, this inner horizon actually, becomes something that's singular itself. So there's some horizon outside, which is the outer horizon, these solutions of course exist provided m is greater than or equal to E. And if you have m is smaller than E, then there's a naked singularity. So anyway, before that, the case with m equal to E is called the extremal Rice-Nostrom black hole. Case with m equal to E, extremal Rn. It's believed that you can't, get black hole solutions which have m smaller than E. Okay? And if you had such a solution, it would have a naked singularity because it would not have a horizon. There's no real roots then. So it would still have the singularity at r equal to 0, but it would not have a horizon to protect that singularity from the rest of space. And so such a solution would have a naked singularity, and so it's believed that you can't form black holes with mass m smaller than E. Okay? So now, someone yesterday was asking me about fundamental particles being black holes. But here's another tutorial question. This is the third tutorial question, I think. Okay. So take Riesper factors of G and C. So you get a dimensionless number and Newton's and of course epsilon naught. Yeah. Whatever units you like to use. So Riesper factors of G and speed of light and everything else that you need to introduce to make this a dimensionless number in some SI unit, and compute this ratio m by E for electrons and protons. So electrons and protons are also objects that have mass and charge. The Rice-Nostrom black hole is also something that has mass and charge. I'm claiming you can't have solutions for Rice-Nostrom black holes which have m smaller than E, but I want you to check what the this ratio m by e is for fundamental particles, for electrons and for other particles. Okay, so this is something you can check. It's a simple enough question, and maybe we can discuss the answer that you could. Okay, yeah.
This is total charge of the black hole?
Yes.
So,
Yeah.
Reina dots from black hole being extremal, that's a very unstable situation, right? Like charged test particles can come and destroy the electron.
Good. So you have to compute what m by e is. Let's discuss this tomorrow. You know what happens if you have extreme. It's true that. Well, okay. Let's discuss. Yeah. Okay. So so actually I'm at 12:30. So I wanted to. Are there any other questions about this solution? I wanted to write down one more solution. Maybe I'll write down the solution, and I'll say a few words, and then I'll stop. It'll actually be a natural point to stop. Okay, so maybe I'll write down the solution since we're already at this point. Sorry, I'll just take 5 minutes more and then we'll stop. So the other solution which is useful to consider is what's called the curl black hole solution, which is a solution that has actually what I'm writing down right now is a charged curl black hole solution, which is a solution that has mass, charge, and angular momentum. Okay. That solution is the following solution. So it's a substantially more complicated solution you can see than the solutions of the Raison-Armstrong black hole and the Schwarzschild black hole, and that's why these solutions were discovered, in fact, relatively recently, in the 60s. Okay, so these solutions are much more complicated, but and in these solutions, squared. Okay. And these solutions have angular momentum, which is they have mass m, and they have angular momentum, which is ma. Okay, so these solutions are written in terms of parameters a and e, okay, which appear here, and these auxiliary quantities sigma and delta. But they have charge, which is e, and they have angular momentum, which is m into a. So that's the angular momentum. And once again, angular momentum is defined by looking at the asymptotics of the geometry. So you look at the asymptotics of the geometry, and from the asymptotics of the geometry, by looking at the cross terms between dt and dxi by going to some key xi coordinate. By looking at the cross terms between dt and dxi, you can read out the angular momentum, and that's defined as it turns out to be ma. Let me just say this guy also has solutions. Once again, has horizons and also has an inner and outer horizon as we discussed. This also has an extremal limit. The extremal limit for a charged curl black hole is m squared is equal to e squared plus a squared. Extremal curl. Okay. And curl black holes beyond this bound are not believed to exist. Let me just say one thing about the astrophysical significance, and then I'll stop. The reason these solutions are important, in particular this solution, even though it's the most complicated solution, is important is the following. In fact, this solution with charge z equal to 0 is what really corresponds to astrophysical black holes. And the reason for that is when you look at accretion disks have the property that they tend to spin up black holes. Okay, so you have black holes which really exist in the world, which correspond to spinning black holes. not these, in fact, there are these black holes in our galaxy you can observe and you can try and determine their spins. And some of them are in fact spinning black holes that have the property that M is almost A. So they are in fact very close to being extremal. They're almost extremal black holes, and these things actually exist. On the other hand, black holes which have just bare charge sitting on them are astrophysically unlikely because charge tends to neutralize. Okay? So you don't have free charges sitting about. If you have some free positive charge sitting about, generally that will attract negative charge and charge tends to neutralize. But angular momentum doesn't tend to neutralize because of the way accretion disks work, and therefore curved black holes are astrophysically important, especially when you set E equal to 0. They have many other interesting properties which we will discuss tomorrow or day after tomorrow. And of course, the last thing I want to say today is that, which I'll again discuss more tomorrow, is that in fact this solution, this charged curve solution that we have on this board, is the most general, stationary black hole solution that you can write down for Einstein's equations. This fact is called the no-hair theorem, which tells you that in fact black holes have no hair. Black holes can have a mass, they can have a charge and an angular momentum, and there's no other property that these black holes can have. You can't write down black holes with curved horizons or some exotic horizons, or black holes that in general you might have thought you could write down black holes which have some horizons that are shaped like this bottle, and one more black hole with a horizon that's shaped like something else, but you can't. There's a theorem that tells you that this is the most general stationary black hole solution you can write down. And even if you start with something more complicated, eventually it decays into this solution because of gravitational radiation. And therefore this is an important solution because it represents the end state of all black holes. Okay, so this is all I have to say, and we'll continue.